means that you're testing whether mu, which is the mean function or mean vector in regression, whether that is a restricted subspace of this image of x or LA of x, sorry, L of x. And so the idea was that we fit the restricted model and we fit the original unrestricted model, and we get two residuals, E and EA, and we have this Pythagorean theorem, which relates the size of the residual sum of squares in E and EA, sorry, in the fitted full model and then fitted restricted model. And based on the distance of mu hat and mu hat A, which is this distance squared, which is this term, or equivalently based on the difference between these two residual sum of squares, we can perform a test. So we had some sort of argument that this is a good thing to do. In particular, in the noiseless case, you can figure out exactly whether the alternative is true or not by looking at the difference of mu hat and mu hat A. In the noisy case, we have to come up with a way to measure how big this is, or how big this should be for us to reject. And that is where this result came into play. So we saw that under the null, we have an interesting, or we have like the exact distribution of this quantity, which is chi-squared. With q degrees of freedom, q was the number of constraints that we put on betas. And this guy is also independent of the residual sum of squares in the full model. And based on this information, we constructed a test statistic which does not involve any unknown parameters. So this is good, but the issue is that the sigma squared is unknown. So we did the usual thing to divide by, instead of by sigma squared, we divided by s squared, but then you have to manipulate this a little bit so that you have a quantity whose distribution is well known. And so in the end, we settled on this F statistic, which is really simple to compute. So you look at the difference of mu hat and mu hat A, the norm squared. So this is sometimes called extra sum of squares or additional sum of squares. It is also equal to the difference of the residual sum of squares for the two models. And this divided by Q, which you can think of as the degrees of freedom of this. This is also another sum of squares, the additional sum of squares. And then everything divided by the residual sum of squares for the full model divided by its degrees of freedom, which is the sample size minus how many parameters you have in the model. And this turns out to have an F distribution under the null. So I can use this to build a test, set the threshold such that I have a given alpha. You can also compute the p-value and compare the p-value to the alpha that would be equivalent test, as we discussed before. So we did this example where we had drugs given to people. And one of the interesting points of this example is how you set up the regression problem. There are different ways to set up the regression problem, but the way that we did was we set it so that these betas are the effects of drug on the cholesterol level. All of this setting up is some sort of a has some sort of an implicit assumption. So you're assuming that the like final cholesterol level is a linear combination of the initial cholesterol level plus basically constant times the effect of that particular drug. So, and then plus some noise. So based on this assumption, we have this regression model, and these xi's are indicator variables. So they're active in each individual. Exactly one of them is active. So there's 0, 1. And we tested this hypothesis that all the betas are equal. That would give me the 5 betas. That would give me 4 constraints, 4 independent constraints. The way to set up the restricted model, a simple way is to assume all of them are equal to some gamma, and then I can plug the gamma into this equation, and things simplify to. So I'm calling this. This is the last time I made a very brief mention. So I'm calling this model M. We can think of it as one model. This is basically the biggest model that we're going to work with. When I impose this restriction, I'm basically looking at a submodel. Submodel in the sense that so it's imposing a particular structure among betas. So for some particular, so you can think of this model as the distribution of y as alpha and betas vary. So if you have seen like 200B, statisticians work with parametric families of models. So this is a model parameterized by 1, 2, 3, up to 5. So 6 parameters, 6 free parameters. So you can think of this as a model with a parameter in R to the 6. And that parameter is free to like move around in the parameter space. So the parameter is parameterizing the distribution of y. So you get basically y is normal between x beta and sigma squared I. So this is the family of distribution parameterized by beta. Beta here means the entire thing. So once I impose restrictions, I'm restricting this parameter to a subset of R6. So the model that I have now is a restricted subfamily of these. So not all of the things that look like this, but some of the things that look like this for certain betas. So in that sense, you can think of this as just creating a submodel. And in fact, when I plug everything in, their end result is like that. So remember when we like constructed this, because of the particular form of the x's, when I said beta 1 up to beta 5 equal to gamma, I'm effectively summing all the covariates. And you recall the structure, they're all either 1 or zeros, and the zeros and ones do not overlap. So once you add everything up, you get the vector of all ones. And so we end up with this model. I'm calling this M1. This is a submodel of the original model. This is achieved from model M by restricting some of the parameters. So you can't freely vary in R6, but you're effectively working with a 2-dimensional, let's not call it R2, but I mean, in its own, it's like a model with just a parameter in R2. But you can also view it as a submodel. So it's just it's the submodel of the model. So something like all the probability distributions for y, such that beta is in R6, and beta is like alpha, gamma, gamma, gamma. So that's the submodel of the original model. The original model is like all the distributions that look like this for y, where beta is in R6. In any case, so if you want to like view it, if you have seen it, I don't know if you've seen it in 200D, but you define probability families of parametric families of probability models, and statisticians work with these. So you can think of this is model M, this is model M1. You don't have to worry about like the formal way. It's just that this is a smaller model. Okay, so it's really intuitive. So like this does everything, like this guy does everything that that could do and more. So if I manage to fit this, I'm gonna necessarily do a better fit. Whereas this guy does not have that much freedom. It's a proper submodel. Not every model that has like 2 parameters is a submodel of the other guy. But this is a submodel because I directly get this by putting certain restrictions on the parameters. And then later we did another reduction, which was, then I wanted to test gamma equals 0. And basically can ignore the gamma then. You just want to test whether beta 1 up to beta 5 are 0. So the resulting model loses this part. So you set gamma equal to 0. Now you have another model which is even simpler. That's the M2. Okay. So we ended up having, let's see if I have it here. So we have M, which is Y alpha Z plus beta 1, X1 plus beta 5, X5 plus epsilon. And then I have M1, which is Y alpha Z plus gamma 1 plus epsilon. And then a smaller model, which is Y equal alpha Z plus epsilon. Okay, so this is gets progressively more restricted. And so sometimes I write M is like M1 is included in M. And so there's this direction. And so you can think of an F-test, the general F-test that we have, as a way of comparing these models for performing pairwise comparison. So what we did, basically, you start with a bigger model. And when I want to do the hypothesis that all the betas are equal, I'm basically comparing, I'm assuming that this is going to be my null. So under the null, the submodel is actually this. So I fit this original model and the null model and basically compare them. That's what happened. So we did the I'm going to call it SSE. That's the residual sum of squares or square sum of error. So these things are called SSE of the model. So what we did for the first model, that was the calculation that, so that's the model for model 1, and for model 2, for model, the original model we have like 2505, for the other one we have 29. Currently, basically you fit each model individually. For the third one we have like something like this. Seven. Okay, so this is basically the residual sum of squares for each model. And then based on these values, I can compare them. So the F-test comparing these two is basically assuming that this is the null. We assume the restricted model to be the null. So then what I have is the difference of these SSEs. So that's the extra sum of squares. And then divided by how many constraints are needed going from this to this. Okay, so this had like 6 independent parameters. This has 2. Basically, I lost 4 independent parameters. So what I get is something like this on the top. And then I divide by the SSE of the full model, which is on the top, divided by sample size, I believe, is 50 minus the number of parameters, which is 6. So that would give you the F statistic for this, and then you can compare it. So this is F hat. So the distribution of F hat is F with 4 and 44 degrees of freedom. And so you can compute the p-values and so forth. So when I try to do the comparison of these two models, I'm effectively doing a different hypothesis test. So last time we did like the hypothesis testing approach, but now I'm sort of viewing it as a model comparison. So effectively, if we test this hypothesis, it's like equivalent to comparing these two models. But in any case, so this would be the null model. So we're comparing this guy to that, and F turned out to be like this guy, which is the SSE of that, minus the bigger model, and then divided by how many degrees of freedom? 5, divided by the same thing. So the same thing here, because we're comparing the same. Okay, and so the first one turned out to be 1.8587, the other one like 3.4, the p-value. So here f hat would be like f 5 and 44. So the p-value turns out to be 13. And here the p-value turns out to be 0.02. So what we do is, so reject at level 0.05, reject null, do not reject null. So when we don't reject the null here, we basically, in comparison of these two models, we keep the null, which is M1. And then in the second one, we compare M2 and M. We reject the null, so we go in favor of M. So sort of M2 is better than M. M1, sorry, M is better than M2 at level 0.05. Sort of, this is like rough. Don't say it like someone outside class, but like you can do this. Like M is better than M2. M1 is better than M. So you can think of the result of the F-test as a comparison of these models. So M1 is better than M because we failed to reject M1. And M is a better model than M2 because we did reject M2. But there's another comparison that we can make here. If you really want. What else can I do here? Someone? Yes, I guess you guys wanted to say the same thing. Oh, yeah, so I can do that. So how can we do that? Can we do an F-test here? Why? Why not? That's a good answer. So there is some assumptions in the F-test. Okay? So the thing that I wanted you to answer is because one is a submodel of the other one. I can't compare two models that are not. There's no submodel relation. First, they have to be linear models under the assumptions that we have, and one has to be a submodel of the other one. So M2 is a submodel of M1. How can I know that? Or how do I know that? Yeah. So far we're talking about M1 is a submodel of M. M2 is also a submodel of M. There's no reason that M2 has to be a submodel of M1 necessarily. Sorry? Right, I said that here. Sorry, yeah. right. But the idea is that, yeah, so even if I didn't say it, this can be derived from this by setting some of the parameters to like, here is 0, but in general, putting some constraints on the parameter. So if I put this constraint on this parameter to be 0, I get the other model. So that means that the other model is a submodel of M2. If, for example, M1 is a submodel of M, and M2 is a submodel of M, it's not necessary that M1 and M2 are submodels of each other. Can you think of a case where that would happen? So I get two submodels that are not comparable as submodels to each other. Yeah, that's it's yeah, okay, but yeah. Okay, good. Yeah, so for example, I can set beta 1 and alpha to 0, I get a submodel. And then another submodel is like beta 5 and beta 4 equal to 0. Both are submodels of M, but they're not submodels of each other because I can't get one from the other by restricting some of the parameters. So another way of saying what you said is that the relation is not a total order. So it's like a partial order. So you can't necessarily compare every two models when you get models by this restriction procedure. In any case, so because M2 is a submodel of M1, I can do the comparison using an F-test. So which model I should take as the null hypothesis? Yeah, so the way that we sort of devise this test is that I start with a bigger model and then want to test some restrictions on the parameter. So when I put restrictions on the parameter, I get the null model. So this is going to be the null model. So basically, the null hypothesis would be in M1, set gamma to 0. So that's, and then the alternative is whatever, just the M1 itself. So how do I write the F statistic here? Yeah, minus 2930. Yeah, so this, which is the SSE of the restricted model, this is the SSE of the full model now, because that's the full model in this context. And then divided by, so you're not sure? Anyone is sure divide, what should we divide by? Do you like to answer by questions? Are you sure that's one? Yes. It doesn't have to be written, but yeah, let's say if even if we don't write it, why is it one? Why? Okay, good. Because there's one constraint, there's one independent constraint. So one constraint is usually independent. Um, then how about the denominator? 2930 divided by 50 minus 6. Right? Why? Right. So your full model is now this. So you work with the SSE of this, and the number of parameters in this model is 2. Right. So the SSE is 2 by 2930, and then n, the sample size is the same, but the number of parameters is 2. So you don't have to worry about this model at all. So there's no mention of that here. And this has like in F 1 and 48 degrees of freedom. So someone computes this while I bring up the next set of slides. And tell me whether you reject or not. Any like? Yeah. 4, 5. Okay. And the p-value? So did you guys get 2.45? We don't know. We hope, but let me find my p-value myself. What is the p-value? Yeah. Yeah, I guess that's correct. I got like 0.069. Someone else can corroborate this, hopefully. Is 3.45 correct? It's sometime before. I forgot to actually just double check. Yeah, okay. So what do we conclude? At level 0.25, do not reject, which is actually what we hope. Not reject. Do not reject null. Do not reject null means that we keep M1. So all evidence are pointing that M1 is a good model. Okay. If you reject it, then you would, oh, sorry. That's actually, no, sorry. You do not, sorry, that's bad. Okay. You do not reject, so we keep M2, right? So there's a little bit of conflict here. So we would like to not, we would like to point out that like ideally we would reject. So when we compare M1 and M2, we would reject you point to M1. But if you didn't do wrong here, there's sort of, I thought the result would be reject, but okay, like at the border of 0.05, yeah. What should we divide by? Let's see what. Let me remember what the numbers are. So 2930 is the SSE, or Israel squares for model M1, right? And we are doing this comparison of these two. So this is our full model, basically, right? So the SSE for that goes So let's get to this. You're saying why this is here? So if you go back to this, what goes here is the SSE of the full model, right? So the SSE of the restricted model minus the full model on top divided by the SSE of the full model. So here the full model is M2. Sorry, the full model is M1, so that's the SSE of M1. And the restricted model is this. So you get, this is the SSE of the restricted model minus the full model divided by which one? You're talking about here? Oh, yeah, okay. That's right. 2505. But that's, I guess, the numbers I copied from here. Yeah, you're right. So that was not correct. But yeah, thank you. But the conclusion should be the same because I actually have the information here. So this is wrong. Minus 6. So this is wrong. Yeah, I believe what I had on the slides is wrong. We'll check it, but this is wrong. So this has to be 2. And then we run into like a contradiction in statistics, which is perfectly fine. Statistics is not supposed to be. So this is fun. So once you do a lot of things will go wrong. This is a good place to say that once you do a lot of the tests, you don't have to like necessarily be consistent. I mean, this could happen. All of these tests are supposed to like, there is some probability of rejection and rejecting the null correctly. And there is some probability of accepting the alternative. So there is some error everywhere. And so for this particular data set, it could be that you get inconsistent results. You compare like this to that and this to this and this, so things wouldn't. So this is like maybe like it's not inconsistency, but between these two, there's not much evidence to reject M2. But let's say between these two, there's a lot of evidence. And between these two, there's not much evidence. So you have to interpret this yourself. It's a little bit of a interesting topic. We do not reject at level 0.05. So this procedure, this approach is sometimes referred to as model selection. We'll go back to this later. If you change your significance level, if you make it a little bit higher, you would have rejected the null, and like at level 0.1, things would have worked out. So sometimes they increase the alpha to be able to do a better model selection procedure. But I'll leave you to think about it. If you have questions, let me know. But what these tests are supposed to say is at the level of evidence, which one you prefer? Do we want to stick with the null? We don't have enough evidence to like between these two. If everything sort of depends on the threshold that you pick. If you really want 0.05, we don't have that much evidence to reject. The point is, if you repeat this experiment many times, if everything is correct, So even if the true model is this, only 5% of the time you have rejected. Sorry, even if the null model is this, you have rejected incorrectly. Okay, let me not talk too much about this. Questions? Comments? So let me. You guys need the slides, or can I want to sort of go to the next batch of slides. There are some things that I mentioned here, which is like these calculations of these dimensions. These should be like straightforward. There's some sort of linear algebra arguments there. They're not needed as long as you understand the things that we discussed. So maybe, okay, maybe say a few words about this and then move on to the next batch of slides. So you can think of the procedures that we were doing as sort of moving back and forth between linear algebra and statistics. So think of we have been thinking about like a linear regression model as basically providing a model for the mean vector. So a model for the mean vector is basically a subspace. So our model is basically, in the statistics domain, it's a model. In linear algebra, it's a subspace. And restrictions of models corresponds to subspace relation. So M1, for example, is the subspace of M. It means that the subspace that this is imposing on the mean, or the subspace that this is imposing on the mean is a subspace of, so that LA of X is a subspace. So submodels relation is a subspace relation of linear algebra. Fitting the model is like projecting onto the linear subspace. And this thing, which is residual sum of squares, or like the error of projection, this you can think of as unexplained variation by the model. Maybe say a few words about that. So in this, okay, here. So in this equation, that's the Pythagorean equation. You can think of this as the residuals are the variation in y that are not picked up by the model. So this is saying that the variation that's not picked up by the restricted model can be decomposed into two parts. One part, this part is basically explained by the more complicated model. And this is what is left over, which is not even picked up by the full model. Okay, every time you fit a model, you like explain part of the variation. So the model fits part of the variation. There is some part which is not, basically this residual is orthogonal to your subspace. So you didn't pick this up at all. If you fit a more complicated model, you like be able to like explain part of that unexplained variation, that EA. So you can see it here as well. So you basically, so when I fit, when I project Y, the variation in this is like picked up by that, but this is the unexplained part. When I fit it to the like, or project it to the larger subspace with the bigger model, I decompose this into two pieces. One is picked up by the new model, and so basically these two add up to this, which is the our new estimate of the mean, and part which is left unexplained. So every time you project, there's some part which is unexplained. And if you do more complicated models, more supersets of your original model, you keep subtracting from that unexplained variation. But at the end of the day, unless you hit the number of parameters is the same as the number of samples, before hitting that barrier, you still have some unexplained variation. So think of this like as projection errors from linear algebra or unexplained variation in statistics. Does that make sense? Okay. The models, every model sort of explains some part of the data. Explanation means you like provided a subspace that captures some of the variation in Y. But there is some part that sticks out, which is the unexplained variation of the error. Let me stop. Okay, now I'm going to do a couple more examples. These are all special cases of the general F-test. I'm going to do it quickly because now hopefully you understand what is going on. It's very simple once you understand. Many of these things that people do are just special cases of this. So I have a regression model here. And you want to test whether the linear part is there at all or not. So the intercept is usually benign, so you keep it in the model always. But the key part is whether there is relations between the covariates and the response. Is there anything at all? So to test that, I can test whether all these coefficients are 0. And if I do that, that will be my null. The restricted model turns out to be just this. Okay. So I fit the original model, I get an SSE, and then I fit the restricted model. But because this is very simple, the answers are sort of obvious. So what would happen if I tried to fit this model? What would I get for beta not, let's say, beta not hat in the restricted model? Let's call this M0 if you want. M0. What would it? Yeah. Yeah, great. So it would be just the mean, just the sample mean, the coordinates. And you can easily see this is, you can use the formula. The formula is like X transpose X inverse X transpose Y would be like 1 transpose 1 inverse 1 transpose Y. This would be N, right? And this 1 transpose Y would be just summation I from 1 to N. That's basically this guy. But the idea is like intuition is correct. So the regression coefficient is just going to be the sample mean. And how about the SSE for this model? Let me call it. What would that be? This is like Y minus that beta hat not. Sorry for the horrible notation. Avoid confusion. So that's the yes, and so we square. What is it? It's fine too. It would be summation I from 1 to N something squared yi minus y bar. Okay, so this is a vector of y1 up to yn. This is like y bar times 1. So this is the SSE or the restricted model. This is oftentimes called SST. Okay, so total sum squares, something like that. So it's nothing but the residual sum squares for the restricted model in this case, but people often don't call this a model because it's too simple. So it's just, you can think of it as total variation in y. So how this is measuring how far y is from the sample mean. You can think of it as if I divide by 1 over n, it's actually an estimate of the variance of y. Okay, so so this is going to turn out to be like SST in this case. This is, as usual, called SSE. Sum squares of error for the full model for this guy, and the difference, which is what goes in the numerator of the F-test, in this case, is called the regression sum squares. So this is called SSR. Okay, in this particular case, these are called. So this is a measure of how well the regression is doing. So And then you would write these in a table, oftentimes called an ANOVA table. So you have the SSE, which is just beta hat is the estimated coefficients for the full model. SSD is just this, and then SSR. There are a couple of formulas for this. You probably write them in your homework problem. It's just you can also like subtract SSE from SSD or compute it directly by these formulas. It doesn't really matter. It's just everything is just as it should be. So there are different ways that you can write this, and then when you write these, then you also have the degrees of freedom, which is again what you already know. This is n minus p plus 1 because p plus 1 is the number of parameters in the full model. This is n minus 1 because the number of parameters in the restricted model is just 1. So that's remember this is the SSE of the restricted model. So you get n minus 1 for the degrees of freedom. And the degrees of freedom of this is just the number of constraints, or the difference between these two. The number of constraints here is p, because we set exactly p of the coefficients to 0. So you can think of them as beta 1 equal to 0, beta 2 equal to 0, up to beta p equal to 0. That's p independent, a set of p independent linear constraints. You can see that they also add up. P plus this would give you that. And then you compute the mean squares, which is just this divided by p, and this divided by this, and then you divide these two to get there. This is all what we have been doing. It's just sometimes people like to write it in a table. Whether you want to do it or not, it's up to you. So that's the form that it takes, but there's nothing there to remember as long as you understand what's going on in general. So they're just some of the names might be helpful. Otherwise, why it's called ANOVA, analysis of variance table, because you're decomposing the variation, as I mentioned. So you're decomposing the variation in the y into two pieces, one that's picked up by the regression, the other part that's left unexplained by the full model. So SSE is the unexplained variation in the full model. This is unexplained variation in the restricted model, which is just the intercept model. Difference is what is picked by the regression. So it's a form of decomposition of variance, which is basically what we're doing. Okay, so this, you can see clearly this is a form of variance. If I divide by 1 over n, or actually if I divide by 1 over n minus 1, it would be an unbiased estimate of the variance of y. And this is similar to, so unbiased estimate of the variance of y, because you know, sort of, this is like the s, this is like s squared, right? In the restricted model, you know that it's unbiased. Or so if I fit this model, I get the SSE divided by n minus the number of parameters, which is 1. I get an unbiased estimator of the noise, the variance of the noise, which is also the variance of y. So I get that this is an unbiased estimator of the variance of y. So we're really decomposing the variance in a sense. Does this make sense? Question? Sometimes this is called testing for the significance of, did I mention this somewhere? Yeah, so I mean, you'd see that if they ask you to test for the significance of the regression model, this is often what you want to do. And this is reported in LM command at the end. There's like a value f test that you see. This is what they say. You want to test whether actually there is a relation between y and x at all or not. So the complement of this logical complement is that there exists one of the betas that is non-zero. That means there is some relation. Otherwise, there is no relation, at least linear relation. So it tests for the significance of the linear relation. What else can we do here? This special case has other interesting consequences. Again, that Pythagorean theorem, in this case, would be SST equal SSR plus SSE. Right? This is like EA, and this is like E, this is like mu hat, and this mu hat A. So I have this Pythagorean theorem, and then I can divide both sides by SST. So if I do that, I get 1 is equal to SSR divided by SST plus SSE divided by SST. So this tells me how well the regression is doing. This is the unexplained part. Right? So this thing is called R squared, as you probably know. And it's also 1 minus the SSE divided by SST. You can see from this, and it's just a restatement of that Pythagorean theorem, which is a consequence of the projection business. So again, because these are all non-negative and they sum to 1, they're going to be between 0 and 1. So this is at most 1 and at least 0. When it's 1, it means that basically SSE is 0. So there is no unexplained variation. Your model perfectly fit the data. If it's 0, it means basically your model is useless, or not useless, but there is no relation. Okay. And somewhere before it hits 0, your f-test would reject, because the f-test, if it's 0, the f-test is gonna, is gonna like pick the null. The null hypothesis that there is no relation. But even if the SSR is small, not 0, at some point this is gonna fail to reject. So you're gonna say that there's nothing there, although there is something showing up here, but the statistics telling you probably have to not reject if you wanna like be careful, like have 5% significance if you repeat the experiment. In any case, this is a good measure of fit. So how well your model is fitting. Right? So you already probably know this, right? You know R squared. People. How many people knew about R squared? Okay. Seems like you have taken your courses seriously. So it's called coefficient of determination. So we can say a few things about this. So it's a measure of the strength of the linear relation between y and x. This is a little bit subtle. So so it doesn't tell you, for example, that these betas are necessarily large. Okay. It doesn't mean, for example, suppose you have a regression line. So you have like a data like that. And then you fit your model. This is like a simple regression. So there's just one covariate. And you have y. And so beta hat here is quite large. Beta hat 1 would be like, let's say, close to 45, for example. This is one case. And then another case I might have that this is x, this is y. My data is like, there's a very narrow thing here. So the data is like this. I fit this, the regression line would be like, beta hat 1 is probably like 0.1. So the effect, this is sometimes called, these betas are called effect size. So the betas are effect size. So this has a bigger effect size than this. But which one do you think has a higher strength of the linear relation as measured by R squared? Is this higher? This one? Why? Yeah, okay. So yeah, so this is gonna be higher, even if like very close, it was very close to the x-axis. The slope doesn't matter. How well you're concentrated around the line matters. So because the residuals are small, much smaller, this is gonna be smaller relative to the variation in. So it's relative to the variation in y. Variation in y is measured like in this direction. So how far away you're from this line relative to the average. So the average, if you look at the average, basically you look at the SST is measured like this. So you take the average value of y and then how far away these points are from the average value. That's the SST. And the SSE is how far away you're from this line. So the variation around this. So this is going to be quite high for this because you're very noisy. So this is going to be this is going to be close to this, and so your R squared is going to be small. Whereas this, your y might be, so the average might be something like that. So around this, but then the SSE is like how much you vary along this line, and you're very tightly closely like following the line, and so the SSE relative to the SST would be much smaller. So it doesn't care about the size of data. It cares about how well the model actually fits. So it's a very good measure of that. Yeah, it's a little bit hard to say, but I think about this. It's important. Is this sort of clear? Okay. So in the noiseless case, you're going to have perfect. If you had the model, the linear model, and there was no noise, then you would have the perfect R squared is equal to 1, even though beta could be very close to 0. So it's just how relative to the line, how much you vary compared to the total variation y. So if the slope is close to 0, the variation in y is smaller. But it could be that you're even tightly close, like more closely related to, or more closely follow the line than the total variation in y. Okay, so this is a subtle point, just pointed out. You can add and remove variables, and the R squared is going to change. So if I, so you know that if I drop every variable here, I get this. I can then reintroduce variables one at a time. So I can introduce a model, which is a little bit complicated, beta 0, 1 plus beta 1 x1 plus epsilon, and then go to another model, which includes both x1 and x2, and so on. So these get progressively more complicated, and they're all sort of super models. Or this is the first one is a submodel of the next one, and the next one is a submodel of the next one until you hit this, which is the supermodel of every one of these other models. So in this procedure, what do you think happens to the R squared? If I try to fit this model, does the R squared go up relative to this or go down? Yeah. Okay, good. When you add features, R squared increases or like stays the same. It doesn't decrease. Sorry, it doesn't decrease. So can you explain why? Right. So that's the idea. So if you want to argue it from the geometric perspective, the thing that's going to happen is that you start from something like that. So you have the SST, you fit one model, you pick up some of this here, and the rest is there. Now, if you add one more variable, what it does is that it splits this into two parts. There's going to be another new SSR type. I'm not going to say SSR, but there is something that goes here. And then what is left over. And this part gets added to this. So the sum of these two would be the SSR for the new model. Right? So if you think of the projection, all of this makes sense. If you add another variable, you're going to split this into two pieces. This is the unexplained part. The explained part of it, parts remain. And so you can write a big, giant Pythagorean theorem to get the sum of these things. The thing is that the SSC of the newer model is going to be necessarily smaller because all these terms are positive. So you're keeping you keep decomposing basically. You keep decomposing until at some point there's nothing left. So at some point you explain everything, and then you get zero. That's where you can say we have perfectly fitted. Some people say overfitted with the data. So when does that happen? Usually, when do we hit zero? As you add, you have the answer here. Yeah. Yeah. So because then you also have an intercept, you get exactly. So if I have p equal n minus 1, because usually I also have an intercept, p plus 1 would be n. Okay, the total number of parameters is n, and the sample size is n. And then you can go ahead and see what happens in the regression. It's really easy to figure out, because then in that case, x is going to be squared. A square matrix, so I can actually, this, which is usually, you can't simplify. In that case, you can simplify because x is squared, so the inverse goes in. So you get x inverse x negative t, and you get x ty, and these two cancel out. And so you get x inverse y. Okay, and then I'm assuming that x is full rank, so it would be invertible. And so mu hat would be x theta hat, so you get x inverse y, and so you get y. So you're projecting basically onto Rn, and you get back y. Y is in Rn, you're projecting onto the whole space. And so you get like y, and E would be just y minus y, which is 0. So the SSE is 0, and then we're done. Okay. But this is not necessarily a good thing, right? Why it's not necessarily a good thing? Yeah. Right, good. Yeah, so the issue is that the way we think of these models, that they're models for noisy data. So if there was no noise in the data, then this would be fine. But if I believe that there is noise in the data, so if you believe that your data is noisy, so yeah, unfortunately, I don't have time to explain this very well, but you can think of like polynomial regression, if you have seen it, as let's say if I have one variable, but I want to fit a nonlinear function, like usual linear regression is like this, but I can try to fit a polynomial. So I can introduce man-made covariance. So I can just throw in x squared, which is a covariate I built based on x. So now I'm fitting it like a quadratic function, and I can keep doing that. So I get supermodels basically, which are basically more complicated, right? So I can start fitting these, and once you do that, polynomials are very interesting. They start to like, so the line would like would do something like that. A quadratic tries to do this. A third degree polynomial does that. And at some point, once you hit like n degree n minus 1, you start sort of interpolating. So you go through all the points perfect. If these are the points, let's say, your function is going to sort of interpolate perfectly through your function. But you don't want to do this because you expect this variation to be due to noise, right? So you started to perfectly fit the noise. Later, when you redo the experiment, these variations would change. So maybe this was like this. The actual function is this. The next time you fit it, the points are going to be very different. They're going to be around this, but different points. So this is not necessarily a good fit, because for future or generalization, as pointed out, it's a bad fit for that. And so if you care about prediction, this is going to predict mostly badly relative to this. Yeah, so I can talk about this more. So more recent things in machine learning, some people, if you have heard about deep learning, people like question this. So if it things that are very complicated, the millions of parameters, the billions of parameters, and they overfit, and then they say actually we predict better. So there is some room here to discuss. We can come back and talk about this, but if you have noise, generally it's not necessarily a good idea, especially if you have high noise, high levels of noise. You're gonna perfectly like capture all the like swings that are produced by the noise, but this is probably not optimal. So you don't want to perfectly fit this particular noisy version of your data, because later on the noise is going to change. So there's a tendency to go for simpler models. And this is the question of model selection. When should I stop? How much R squared is enough before? Because I can always increase it if I just. So R squared itself is not a good measure of model selection. So we have to sort of balance it by the complexity. Okay, I'm going to stop. Maybe come back later next time, talk about this as well. Questions? Okay, see you guys next time.